so we can all get to lunch. First, let me say that the Department of Energy is a very large, complex organization, and by and large it is a development organization. It also does some deployment. It's not a regulatory organization at all, by and large. I actually come from the development side, but I'll try to set the stage for what's happening in terms of legislation and some of the efforts that DOE's undertaken in terms of deployment and helping to promote standards. There's actually 4 different parts of DOE that fund energy storage development and deployment. One is the Office of Electricity, which is all forms of energy storage. Then there is the battery development specific to vehicles that occurs under where I'm at in the Office of Energy Efficiency and Renewable Energy in the Vehicle Technologies Program. There's also, started 2 years ago, ARPA-E. ARPA-E has a number of projects for both grid energy storage as well as vehicle battery development. And then underlying that, there is fundamental research being supported by the Office of Science, and they're the basic energy science programs, some of the things that Eric Isaacs alluded to yesterday. So here's the content of the presentation. I'll talk a little bit about the key drivers for grid energy storage. We've already heard about some of that. Then I'll give you an update on what's going on in the legislative world. And then turn to vehicle electrification and look at some of the impacts at a macro level on the overall grid. And then wrap up with some comments on DOE's investment in development and deployment of energy storage technologies. Historically, the grid has been around for over 100 years, and traditionally it's been expected to be a provider of reliable power, affordable power, and to be a secure network. But as we go forward, there's some new expectations being placed upon the grid, and we've heard about some of them already. If you add up all the renewable portfolio standards, there's something like 300 gigawatts of new renewables generation that would go online by 2025. Vehicle electrification, depending upon the success and how much that takes off in terms of market size, could also have a major impact upon what's expected of the grid. And the issue of reducing carbon footprint, carbon tax, that also could have an expectation as far as the grid, although that's a little bit uncertain where we're going with that in terms of climate change legislation or carbon tax or any of that. But I think in general we're moving in that direction. It's a question of how soon that's going to have a direct impact. When you look at the electric power system overall, and you ask where does energy storage fit into that network, it actually fits into all 4 of these parts of the system. We heard a very good talk yesterday about from Joe Heinzman about how energy storage fits into the transmission network, about frequency regulation. I think that's certainly probably the first big application that we're going to see. But it also fits on the generation side in terms of load leveling. It fits on the distribution side in terms of community energy storage, which we talked a little bit about yesterday. And on the customer load side, it can certainly be used to reduce peak demand. So it really applies across the board here in all of these segments. Some of the key drivers for grid energy storage, we certainly talked about renewable integration. Transmission constraints is also an issue. Energy storage can help alleviate some of the problems and issues with transmission constraints. Smart grid is certainly another driver for energy storage. It allows it works in a complementary way with smart grid. Smart grid helps energy storage. Energy storage helps smart grid. And the greenhouse gas reductions, which I talked about on the last slide. Here's a quick summary of the renewable portfolio standards. There's now 37 states plus the District of Columbia and Puerto Rico that have either a mandate or a legislated goal. 29 of these are actual mandates, but they vary quite a bit, both in terms of their timing. Some of them are 2015, some of them are 2025. They vary also in terms of the definition of what is a renewable. Some states consider some things to be renewable and other states don't. Some people have called for a national renewable standard. That may or may not ever happen. There's been people who've advocated a regional standard because electricity by and large is on a regional basis. So maybe that's the way to approach it. But so anyway, there's quite a variety of standards out there. California, of course, was one of the earliest to have a renewable standard and also one of the most aggressive. We're now talking about 33% renewables by 2020. Here's just an example taken from EPRI about the ability of energy storage to provide load shaving as it's coupled with renewables. In this case, they're showing an example of 3 gigawatts of solar. And you can see as solar comes on, where we go, during the afternoon hours, it can provide some shaving of the afternoon peak. If you want to couple that with energy storage, you can further depress that peak, shift that load. But you need several hours of storage. So for this type of application, it's quite different than frequency regulation in terms of the ratio of power capability to stored energy. In terms of reducing greenhouse gas emissions, here's an example of CO2 reductions. In this graph here, excuse me, the graph shows, on the y-axis here, we're showing the CO2 emissions per megawatt hour of capacity generated as a function of both time during the year and both time during the day as represented by peak and off-peak conditions. During those times of the year when you don't have a large air conditioning load, the base load emissions are quite a bit lower than what you see during either peak times or particularly during the summer peak. And this is borne out by a number of data from a number of utilities where typically you'll see about a third reduction compared from the peak to the off-peak conditions. So energy storage does certainly provide a way to reduce CO2 emissions. There's various types of energy storage. Most of these have been at least mentioned earlier in either today or yesterday. There's also one on here that's not listed, and that would be magnetic energy storage, superconducting magnetic energy storage. I also heard something about regenerative fuel cells earlier this morning. I guess my own comment on regenerative fuel cells is that the overall round-trip energy efficiency of those systems tends to be fairly low, on the order of 30 to 40% maybe round trip, whereas batteries can be 80 or 90% efficient on a round-trip basis. You'll also notice that there's variability in the size or scale to which these have been deployed. Certainly pumped hydro has been around for perhaps the longest and is the largest in scale, where we're talking about excuse me, thousands of megawatts. Compressed air is also fairly large in scale, but both of those are largely dependent upon having the right geophysical, geological sites that are amenable to those types of applications. Thermal storage is really not electricity storage, but it does, in a sense, function to the same purpose, in the sense that it is able to reduce, to use off-peak electricity to reduce electricity demand during peak periods the following day. Battery technology has come quite a long ways in recent years, and that's certainly encouraging for future developments. One of the largest ones to date has been the sodium sulfur battery. Shown here is a 50 kilowatt system from 50 megawatt system in Japan from NGK. NGK, of course, is a developer of that battery and has for quite a while. So if you look at the benefits of energy storage, they really affect multiple stakeholders. They affect not only the utilities, but they also affect, there's benefits for the system operator, there's benefits for the customer in terms of lower overall rates, and the societal benefits that I mentioned about fewer emissions and the ability to bring on more renewable sources of energy. But the fact that there are multiple benefits is both a blessing and a curse to some extent. And that has to do with the compensation for the energy storage system. The current regulations don't adequately capture or monetize all of those benefits. Traditionally, the regulatory agencies look at specific asset classes, that is either generation, transmission, distribution, and that's how they build their rate structure. But when it comes to something that spans across those asset classes, the regulations have not yet caught up with the benefits there. And I think there's a consensus that there's a need to capture that, but the devil's in the details, and that's what's being worked on now. You also have a lot of different players involved. You have the Federal Energy Regulatory Commission, and then at the state level, you have a number of different regulatory agencies that are involved, from the PUCs to the ISOs, the Energy Commission, and the Air Resources Board. Each of these have a stake in the grid and the energy storage that would apply to it. And each has certain benefits that they are deriving from the system.